Yeah, so I should start now?
Yeah, that's fine. We are complete now.
Okay, great. Thanks, man. So yeah, I'm Andy Hooper. So I'm professor at the University of Leeds. And I got my PhD from Stanford working on time series InSAR, which is what I'll be talking about today. So yeah, I've been working in this field for well over 20 years now, I guess. Yeah, I think I'll just dive in. Oh, by the way, I'm sorry I'm not there in person for those that are there in person. I'm currently in Chile at a volcano observatory. And yeah, anyway, it's great I can join online. So yes, time series InSAR is what I'm going to talk about. I guess you've had a lecture already on interferometry in general, and atmosphere as well, I believe. So I'm going to be talking about time series InSAR, and I'll start with some motivation. So I will stop at a few. I'll pause along the way to take questions, if that's okay. It's probably easier that way while I'm online rather than shouting them out. And I can't really see if hands are up. Apologies for that. So the motivation. I think there are some obvious reasons why we do time series InSAR, and probably some less obvious ones as well. So I'm going to start with maybe the less obvious ones. So if we look at a good interferogram, like this one, so this is an earthquake actually in Chile, where I am now, from 2015. And it's a good interferogram in a couple of ways, I guess. First of all, there's good correlation. So essentially that means low noise within the image, and you can clearly see the fringes nicely across the interferogram. And secondly, the signal is dominated by the deformation. So there will be other noise terms there like atmosphere. It's not a big issue, right? Because the deformation is dominating. So this is an easy, in a sense, interferogram to work with. So because it's good correlation, we can unwrap it and then just interpret the deformation. Okay, but that's not a typical interferogram, thankfully, I guess, because we don't want that many large earthquakes. In a typical one, anyway, we get signal that tends to be dominated by atmosphere. And some other errors as well, such as errors in the orbits and errors in our DM that we've used to subtract the topography. So if we're looking at slow deformation or low deformation rates, then these signals tend to be larger than the deformation. So we just can't see them if we look at an individual interferogram. And then you also get the added complication that because of decorrelation, we get a lot of other noise. So this is maybe in many cases a fairly typical interferogram that we have to work with. So areas where you can see there's some signal beneath it, which can probably be pulled out, but some areas where it's really very, very noisy indeed. So how can time series InSAR help with this? So first of all, it allows us to sort of select which of the pixels which have better coherence, so we can get rid of a lot of the noisy pixels. And then we can also reduce other errors, such as these atmosphere or orbit errors, essentially through filtering. So we have a lot more data, we can start to reduce these signals by filtering. We can also reduce DEM errors. So for those of you that have been working with Sentinel data, DEM errors are not a huge issue because the orbital control is so good, but they can be, depending on what data set you're working with. The DEM errors can be quite large. Also, having 3 dimensions, it just helps with phase unwrapping a little bit. I'll come back to that briefly later on. And then good aspect, I should say, is that we can do high resolution processing. So we can even get sub-pixel resolution in some cases. Okay, so all those are maybe the less obvious reasons. And then there's the obvious one, which is if we look at time series, then we can actually study time variable processes as well. So just to demonstrate a couple of those points, this is an example of improvement of coherence. So these are the 2 interferograms on the left that I showed already. And if you carry out persistent scatter interferometry, which is a time series method, you can see we can extract the signal the panel on the left looks similar to the original interferogram, but on the panel on the right, you can start to see the signal, which wasn't so obvious before. So we can deal with coherence to some extent. And then we can, as I said, you can try and separate out these other nuisance signals like atmosphere. So these three panels are showing on the left what we actually are interested in, which is deformation. So this is an area in Mexico, and there's deformation due to slow slip on the subduction zone. Then in the middle, that's an example of an atmospheric signal. It's just from one image. And you can see that actually, if you just interpret it without being able to subtract that there'd be some interference with the deformation signal because they overlap almost in space. And then in this case, there was a large DEM error as well, which needed to be dealt with. And on the point of resolution, this is a really nice example. So you can't do this for Sentinel-1, but if you have higher resolution data from some of the X-band satellites, you can really start to get amazing resolution, so you can pick out points on the sides of buildings. And then because I'm in Chile and we were just looking at this morning, I'm showing an example here of a volcano where there was time variable deformation. So on the left, you can see the sort of cumulative displacement over many years. But on the right, you can see the time series just for one point, which I don't know if you can see there's a little green point on the image on the left. That shows the point that we're looking at. So you can see there was a period of substance, then it was uplift, and then substance again. So yeah, and we can then interpret this, of course, with our in terms of what's going on beneath the surface, which is perhaps the whole point of why we look at surface deformation. Okay, so that was all just the motivation. How do we actually do it? Well, I guess there are two principal ways. Some might argue there's a third, and I'll get to that later, but essentially there are two. Persistent scatterer methods, which I'll talk about first, and then small baseline methods, which I'll get onto later on. So persistent scatterer, or PS methods, sometimes referred to as permanent scatterers as well. Why is this the thing? Well, first of all, we have to understand about the causes of decorrelation, and I guess you will have heard this already from Tim. But essentially, the reason we have decorrelation is because within a resolution cell, so within a pixel in our image, more or less, we get contributions from many scatterers on the ground. So they're all reflecting back energy. And it's the coherent sum of all of these. So you could think of it as a little sine wave going down and bouncing back off each of these scatterers. But then it's the coherent sum. So they're all added together, both phase and amplitude, to give the phase of the overall pixel. So this is all very well and good if they behave nicely and these scatterers don't move around with respect to each other, it's fine. But if they do, then you get a change in the phase, and that's without any deformation or anything else. You just get this change in phase just due to relative movement of scatterers. And there's a simulation of that shown here. This is when they're moving around too much, such that you can no longer track the signal. It just looks like random phase. You get a similar effect to if the instance angle changes, which is to say, if you have a large perpendicular baseline between the satellites, if that means anything to you. Okay, so what can we do about it? Well, this is the kind of idea of a persistent scatterer pixel, is that you have one scatterer that really dominates within that pixel or resolution element. Such that even if the other pixels move around, because they're not contributing so much, you can track the phase. So here's an example where I think the difference in signal to noise was 10 here. So the brighter one is 10 times brighter than the others. And then even when the others are moving, they're contributing a little bit of noise, so a little bit of decorrelation, which you can see in this figure beneath. So that's just showing a simulation of 100 different acquisitions. But you can see the phase, you can track it in time. It's approximately constant, and that's the phase of the dominant scatterer, the persistent scatterer. So that's the idea behind PS, simple enough. So how do we actually go about processing to actually extract these persistent scatterers. Well, what we do is we take a whole series of images and we form interferograms, all with respect to one image. Okay, so it's a sort of single primary approach. We do this at full resolution. Yeah, in fact, you might even go more than full resolution using oversampling. This isn't always done, but it can help because it, it means you're more likely to get your PS in the center of the resolution cell. And then we reduce the phase as much as we can. So typically that, of course, involves correcting for topography, mostly. So just a sort of a visual demonstration of that. This is an image showing time along the x-axis and then perpendicular baseline. So the separation between the satellite at the two different acquisition times on the y. And yeah, there's a central point. So the red circles are the acquisitions and the green lines are the interferograms we form. So you can see that all the lines are radiating from one single acquisition. So yeah, they have variable baselines and variable temporal baselines as well. Okay, so here's an example of what those interferograms might look like. This is an example for Mexico City. Yeah, actually, there's quite a bit of coherence and quite a lot of substance going on there. So lots of fringes. Okay, so to understand the next bit, we have to think about what the contributions are to the interferometric phase. And one way of splitting it up is like this. So we have phase due to the deformation. That's really what we're trying to get at. That's what we're interested in. But then we also have contributions from the atmosphere, which you would have heard about already. Something due to orbit errors. So that's just because we don't know exactly what the orbit of the satellites are at any given time, although these days they do tend to be very good. DEM error due to the fact that we don't know topography exactly. So there's always an error in our elevation model, which maps through then to our topographic correction. And then we have, well, I'll just use a catch-all term as noise. Mostly this is due to decorrelation. It can be, there's a few other little terms as well, but it's mostly decorrelation that contributes to this. Okay, so in terms of how do we define a PS pixel, it's really those that have low phase noise over the whole time series. Okay, so if we can identify pixels with low phase noise, we can identify our PS pixels. There are kind of two different ways of doing this. I will cover them both briefly, well, maybe not briefly, but I will cover them both. So let's say the original approach to this, the original PS method is really based on a temporal model, whereas the other one is based on spatial correlation, which I'll get to. So the pioneers of this technique were the guys at the Milan, Politecnico Milan. So Alessandro Ferretti and his advisors. So they call this the permanent scatterer technique. It's an example of a persistent scatterer algorithm. And here's a nice example, early example of this technique being applied to the San Francisco Bay Area. So here, color represents the average velocity. So how do they do this? Well, what they do is they calculate the phase between individual pixels. So you take two pixels that are close to each other, that are coherent, and subtract the phase of one from the other in the time series, in the whole single primary time series, then some of these terms sort of cancel out. So the atmosphere mostly cancels out, and the orbit errors mostly cancel out as well. Not exactly, but they become very small. So what you're left with then is just your deformation, your DEM error, and your noise. The first of these two can be estimated by modeling if you have a good model. So we do have a reasonable model, I think. So the first step, just to step back a little bit then, is to select which points you're going to difference the phase between, right? So you want to pick points which are likely to be coherent, are likely to be PS. And the way that is typically done is by analyzing, first of all, the amplitude in the time series. So you can calculate this something called the amplitude dispersion, which is really just the standard deviation of the amplitudes over the mean amplitude. So this is a per pixel value. And the reason this is used is because it's actually quite a good proxy for phase noise if it's small. So this is amplitude dispersion is shown on the x-axis, and phase noise is shown on the y-axis here. So you can see at the end towards 0, 0, then there's quite a good correlation. So if you stick to just using values, of, below about 0.25, then it's a good proxy for that. Okay, this does present a challenge if you don't have lots of pixels with low values of amplitude dispersion, and I'll come to that a bit later on. Okay, so having selected your likely PS, you then construct this network, which means calculating phase differences between points, so constructing so-called arcs and calculating the phase difference between them. Okay, so then, as I mentioned, that essentially just leaves three things. It leaves your noise, but it also leaves your deformation phase, and it leaves your DM error phase. And we can estimate these. So the deformation, typically a model, you need a model in time, and typically the assumption is that it's approximately linear or steady state in time. So what is typically estimated is just a velocity, but in principle, you could also calculate sinusoidal, seasonal terms, or whatever you like. And then for the DM error, there's a simple model for that because it correlates very well with perpendicular baseline. Okay, so for every phase, every double different phase, every phase arc, what you need to do is model these two terms. This needs to be done simultaneously, but I'll show you individually what that looks like. So in terms of modeling the deformation, as I mentioned, typically it's just assumed that it's approximately steady state. So that amounts to just fitting a straight line to your phase in time, okay, of the phase of the phase arc. Sorry, the phase of the arc. But you have to remember that phase is wrapped. So every time it's going from minus pi to pi, and then it, if you add a bit more phase, then you get down to minus pi again. So it's fitting a straight line to these points with the proviso that you can add any integer number of 2 pi to each data value. So this figure kind of tries to demonstrate that. At the bottom, in the range between minus pi and pi, you can see a line that's going through the points with breaks every now and then. And then you can also see a line where integer values of 2 pi have been added to some of these, and then you get a nice straight line, right, going through all of these points. So that's the idea. You're just trying to find the best fitting line, so minimizing the residuals between the actual phase values and the model. So this is done for every pair of pixels in the network. At the same time, you have to estimate the DEM error, and this time it's a similar thing, but this time on the x-axis, you line them up in order of perpendicular baseline rather than in time. And again, you expect to get a straight line, right? Because we expect our DM error to be correlated with perpendicular baseline. So there'll be a unique slope for every pixel pair, which correlates to the DM error or the difference in DM error for those two pixels. Okay, so once you've done this, you can integrate. So you start at one point and just integrate throughout your network to get these model values for the velocity and the DM error for every point with respect to one single point. And while you're doing this, you can reject points that seem inconsistent. Okay, you have some redundancy in your network, so you can integrate to each point in different ways, and that allows you to actually reject bad points. So here's a very old example of that. And on the top, you can see DM errors. This is for Las Vegas. So some of the DM errors are very high. That's because there were reflections off the top of very tall buildings that weren't included in the DM. And at the bottom, you can see the mean line of sight velocity that was estimated for each of these pixels. Okay, so once you've got this network of good stable points that you think are good PS, you can take the residuals, so subtract off your model, look at the residuals, and then interpret that in terms of atmospheric delay, essentially. You subtract that then from all pixels, and that then allows you to test every pixel by forming a connection, so forming arcs to PS that you've now established RPS. You can now form connections to those PS to decide whether these are PS as well by looking at, having corrected your atmosphere and so on, what are the residuals looking like? So it's a way of estimating the noise. And once you've done all that, you can use filtering in time and space to separate unmodeled deformation from atmosphere. So it's recognizing the fact that your deformation may not be exactly linear, so there may be some deformation on top of that. So you can try and separate that out by filtering. And you get to a result like this. Here I'm just showing the average velocity, but actually you have a time series for every pixel as well. Okay, so it's a nice image. There's lots of deformation here because it's in the San Francisco Bay and there are faults running through. But nevertheless, you can see that we're not getting pixels everywhere. So PS works really well in man-made or in urban areas where there are man-made structures, which make good PS, but not so well in rural areas. Okay, so I'm just going to pause here for any questions. So that can be from the room or online as well, I guess. Let's see if I can actually get hold of the pictures. Sorry, the questions.
Thank you, Andy. So let's prioritize questions from the in-person participants, right?
Yeah.
So I think the microphone captures quite well. So I don't see any hands up. Okay, well, there is one. Yeah.
So persistent scatterers, are there any, like you said just a second ago, you said about it works in urban areas more. Are there any kind of features that in non-urban areas that persistently scatter?
Yeah, that's a good question. And actually it nicely cues up the next part of my talk. So yes, I mean you can get natural objects that scatter quite well and quite brightly. You could think of a big rock, for instance, that's oriented in the right direction. So yes, there are PS which are not. And actually, if you think a bit more broadly about what a PS is, just any pixel that has low noise in the whole time series. So in reality, it can include some distributed scatterers as well if we have a good baseline distribution. So yes, and in the next part of the talk, I'll talk about a different approach which does work better in rural areas. But nevertheless, it works best in urban areas. So that's always the case.
Thanks.
Thanks. Are there more questions in the room, or should I look at some of these online ones? So there's one very general question which I might come back to at the end. Right, here's one. How can we convert line of sight to vertical and horizontal? Yes, I think that's probably best delayed to later as well. How are velocities estimated? Is it the mean? Yeah, so actually in the approach I just showed you, to estimate velocity, that's part of the identification process for PS. So you're finding essentially the best fitting line in time that minimizes the residuals to all the data. So it is a mean velocity. That is correct. What criteria do you consider to select the master image for PS? You kind of want it in the middle. So in the middle of time and also in the middle of perpendicular baseline. How to choose reference points in the area. Yes, so in the end, as with all interferometry, we can only get relative measurements. So you have to choose a reference. You have to refer your measurements to somewhere in the image. So how you choose your reference point depends a little bit what you're trying to look at. But ideally, you're going to pick a reference point that's very coherent and also is in an area where you know what the deformation is. Okay, I might answer a couple more, then I should probably get on. We'll run out of time. My question regarding the PS height, it can give negative or positive values based on DM error. That is true. So actually, the DM error that we estimate, it's relative again. So it's relative to what you already used in your DM correction, but it's also relative to your reference point as well. So it can definitely be positive or negative. How important is the number of images and the time interval? This is quite important. Number of images for this approach to work, because it is a kind of statistical approach, you need something like 20 or more. And the time interval, well, that just, if it's a shorter time period, it's more likely you'll have, oh, the question disappeared. It's answered already. But if it's a shorter time interval, it's more likely that any individual pixel will be persistent throughout that time. So if you get to longer time periods, the number of PS is going to reduce. Okay, I'm going to carry on for now. Maybe we'll have time to come back to those later on. Okay, so I'll talk now about spatial correlation. It's a different approach to get to the same result in most cases. But just to step back a bit, why do this at all? Well, it's to try and address this issue of working in rural areas. So this actually I started thinking about this during my PhD. I was looking at Long Valley Caldera. It's a large volcano or volcanic complex in California. And I applied a PS method, and these were the points I got. So I got some points in a town called Mammoth Lakes, and I got some points on a nice obsidian dome, which turned out to be very coherent, but nowhere else. And actually, I knew the deformation was, more in the center of this caldera. So these results were not useful. So PS in general works well in urban areas and not in rural areas. And why is this? Ooh, I didn't want to do that. Sorry. Can you still see my screen? Is it just me?
Yes.
Oh, you can. Okay. Okay. How do I get that back? Oh yeah. Okay. Sorry. Right. So the reason is you need a good selection for your initial network. You need a good selection of high amplitude points that are likely PS, and that just didn't exist in this case. And another point is that we're typically going to assume a steady state velocity, and if you deviate too much from that, then you're not going to pick your pixels either, and that was the case here as well. So okay, just to move on. What we're looking for then is an approach that can work in rural areas, so where you don't have lots of high amplitude points for your initial network, and also where the deformation rate is not steady state. So the first step in this is the same as the previous algorithm. So you just make lots of interferograms, all with respect to a single primary in the same way. And we get back to this equation again, and what we're trying to do is estimate the noise. And this time, instead of estimating the phase difference between arcs, the approach is to kind of do a spatial filtering. So somehow calculate the average phase around your pixel of interest and subtract that instead. So a simple way of doing this is just to take the average phase of all pixels or all likely good pixels within a certain distance. There are other approaches as well, but I won't get into that. So having done this, if you subtract that off your pixel of interest, then you kind of eliminate nearly everything, hopefully. So if your deformation is correlated, your atmosphere is correlated, your orbit errors are correlated, even most of your DM error can be correlated as well. you just more or less eliminate that, at least reduce it severely. So what you're left with is then just a sort of residual uncorrelated DM error that's unique to that pixel and the noise. And again, we can model this term, this uncorrelated DM error term, in the same way that we did before, but now we don't have to worry about modeling the deformation at the same time, so it's easier. So yeah, I showed you this figure before. This is just, if you just have to deal with this in 1D, a 1D problem, so just fitting data to perpendicular baseline, you don't have to worry about deformation at the same time. And then you estimate the noise from what's left. So yeah, I won't go into how that's done, but essentially you just estimate the mean residual in some way. Okay, and then there is an iteration, because when you do this initial filtering in space, so the averaging of pixels near your pixel of interest that you want to test, then you don't actually know which pixels are good ones and which ones aren't. But having done it once, you've got a better idea. So you can then use this estimate of phase noise to weight those pixels, so you can get a better estimate of the spatially correlated phase. And then you do the same thing again, right? So you can iterate around several times to end up with a better estimate of DM error and temporal coherence, which is the phase noise throughout the time series. Okay, so this then allows you to isolate the noise, which allows you to identify, to choose which are your PS pixels. And then you can go back to those PS pixels and go back to the original phase of that and just correct for this uncorrelated DM error that you just estimated using the model. And you might get something like this. So these are interferograms. These are single primary interferograms, but now rather than showing every pixel, it's just showing the PS pixels. Yeah, for every interferogram. Okay. In this approach, you have to think about phase unwrapping. Phase unwrapping was kind of automatic in the previous approach. So when you fit your model in time, what you're actually doing, when you're choosing how many integer cycles to add to each point, you're actually phase unwrapping, of course. In this approach, you have to do the phase unwrapping separately. And there are different ways of doing that. And I don't really want to get into that too much. I'll just say that we can do better in 3 dimensions, so using time as well as 2 dimensions of space. We can do better in 3 dimensions than we can in 2. So in 2 dimensions, I don't know how much you heard about this when InSAR was introduced in general, but you can connect so-called residues in space. So you integrate around closed loops. Sometimes it doesn't close and you get these residues, and phase unwrapping essentially consists of connecting up these residues in some way and then integrating without crossing those lines. So if you have 3 dimensions, you have a residue in every interferogram. So you can see the time dimension on the y-axis. And these are a bit more complicated because they're sparse interferograms. So the triangular networks represents a sparse network where you just have PS. But nevertheless, you can identify the residues in each interferogram. And you can also identify residues in space-time, right? So integrating around different loops. So you just have more information to help you with your phase unwrapping. You can do a better job. Okay, so this is just a result for the same interferograms I showed you before. So the same PS interferograms that I showed you before having been unwrapped. And then you can do everything else that I already described for the first approach, which is filtering in time space as I already described. So that's just trying to separate out or trying to get a better idea of what your atmospheric signal is and subtracting that. Oh, sorry, I didn't mention that first point. So in the identification step, the spatially uncorrelated DEM error was estimated, but there's still a correlated DEM error left in your left in your phase, which you have to estimate as well. But you can do that much more simply once everything's unwrapped. It's a simple correlation. Okay, so that's it. These are the results for Long Valley. And you can see on the right what you get with this different approach. You get a lot more pixels. So in answer to the question that was asked earlier, yes, you can find PS in rural areas as well. And well, it's always nice to actually know that we're just not just making things up. So there are some ground truth in this case. The PS InSAR results are in red, and then this blue line is showing electronic distance measurements, and I won't get into how this comparison was done, but anyway, there's good agreement. Okay, so that's it really in terms of PS. Just to say that you can do things like come up with some sort of quality index. So one thing you can do is estimate the standard deviation if you assume that you know what the deformation should look like. So if you assume the deformation is linear in time, you can look at you can using bootstrapping, you can try and fit a linear model multiple times, and this gives you a probability distribution, and you can calculate the standard deviation of that, for instance. So that's shown on the right here. So on the left are the actual velocities, and on the right are standard deviations for Bangkok in this case. You'll note that low values are blue, high values are red. The lowest values are clustered around the center. So you'd expect this if your reference is near the center, because as you get further away from your reference point, we expect more and more residual contributions from atmosphere. So that's what we see. Okay, you might wonder why there are these two different approaches. Well, I had to choose between these two different approaches. I think if you're looking at urban areas, it doesn't really matter. If you're looking at rural areas, then maybe it does, and you might choose to use spatial correlation. Yeah, here's just one comparison. Well, I guess the main message is that in urban areas, you get similar results using both approaches. So there have been a couple of studies of this. This is just showing one. And there are occasional exceptions. So this was an example of a housing estate where it showed up. It was a new housing estate, and for whatever reason, it showed up better in the spatial approach than the other approach. But actually, in most cases, you get the same results. So don't worry too much about that. Okay, just a quick word about interpretation of PS observations, because it's nice. You get these high resolution results, which, depending on data set, may only be pixels of just a meter or two, right? Square. So then you can really start to think about where are these reflections coming from? And they might be from the top of a structure, the top of a building. But it could also be so-called double bounce off the side of a structure. So where you have these vertical structures, you can see in the figure here on the left, a so-called double bounce where the energy comes down, bounces off vertical structure, then bounces off the ground, and goes straight back up to satellite. Okay, so you can get very bright reflections from these double bounces. Whereas if it's coming from the top, then really you just have to have the right orientation or some sort of corner type reflector on the top to give you something also that's bright. So why does this matter? Well, if you think about what the deformation source is, there could be compaction of the ground and just the ground. So if we have buildings that have good foundations, the building itself might be stable, whereas the ground is subsiding. And if that's the case, the double bounces will show deformation, but the bounces off the roof won't. Okay, so by looking at these two types of scatterer differently, you can extract more information. And the flip side of that is if you have stable ground but an unstable building, right, you get the opposite. But then in the case of something really deep-seated, so if you're extracting gas from very deep or water or whatever it might be, then everything goes down, right? So both types of scatterer will go down. So there are occasions when it pays to actually think about where your scatterer is scattering from when you interpret the results. Okay, so just to wrap up the PS InSAR, essentially it relies on these pixels that have low noise in the whole time series. So, you know, normally they might be point-like, or at least have one brighter scatterer. You get good results at the highest possible resolution, and we can reduce all the kind of the nuisance signals by modeling and filtering. And it works best in urban environments, although you can get some decent results in rural environments too. Okay, another Q&A. Sorry if I raced through that a little bit. I'm conscious of the time.
So I would again encourage the in-person participants, and we have one hand. Sorry.
Well, actually, my question, you just touched upon it, how we can correlate between the scatterer and the deformation that we are measuring. Can we say, for example, this point that we got as a result, that we can say, okay, we drop the deformation on it, and suppose that we have a building, can we say from which part of the building it's coming? Can we relate the scatterer to the object or to the specific part of the object?
Yes. Okay. So if I understood the question, it's about really identifying what on the ground is causing the scattering. It's not as easy as you might think. I mean, in principle, we can get very good location accuracy if we use so you can do quite good with standard InSAR, but if we then use our DEM error, we can pinpoint even better where the point should be in 3D space. So that is true depending on the data set you have. It's not very easy with Sentinel-1, for instance, because we can't get good estimates of the DM error. But for some X-band satellites, it can be quite good accuracy. So yes, if you're careful, you can get an idea of where it's coming from. And you can separate out ground scatterers from tops of buildings by looking at how height is varying in space. So the ground should normally vary in a very, very smooth way, and where you get sudden jumps in height, then these are probably coming from higher points of buildings. So that's the principle behind that. So it's a little bit tricky. You can do it. The other thing you can use is polarimetric information. So you get these double bounces have a different polarimetric signal to single bounce scatterers. So if you have ideally quad pole data, you can do that, and you can kind of do that with dual pole as well.
Yes, follow-up question. So when we for the special deformation, when we are looking to the surrounding of the pixel, so if I understood it, it would be like a windows, which is like we can define a window around the pixel to do the averaging, and if we like the size of the window that we are looking into, if it's like a 10 meter, 20 meter, so then the result would be also different, right?
I'm not sure if you could just, I couldn't fully hear what you're saying. Apologies for that.
So
Can you?
considering like the like when we are not looking into the 1 pixel, but the surrounding pixel.
Yes, that's right. Yes. So to understand, looking at 1 pixel in isolation, you can't really determine it, but by looking at other pixels around, you can try and separate into different populations. Yeah, that's correct.
And how we can define like this window size or the surrounding? So would be any recommendations about this?
I would probably say it depends. If you remind me afterwards, I can send you a reference, I guess, of where that's been applied, which might be helpful. Yeah, so drop me an email with that question. Otherwise, I'll probably forget, and I'll send you something. Okay. Wow, lots of questions still online. Are there more questions in the room? Sorry, I can no longer see anyone for some reason.
Seems everything is clear here.
Good. So while working with PS InSAR, we might find PS points on the water surface. Is it noise? Probably. I mean, of course, within the water, you can get things that stick up above the water. And I mean, I'm not talking about boats, but I'm talking about something that's permanent and grounded. So sometimes it could be real, but yeah, generally speaking, if you get PS points in the water, then they're not really PS points. They're incorrectly identified. Will there be any differences in results when we use C-band and L-band? Yes, in general, but that really just comes down to the fact that L-band is more coherent in general. So you can expect to find more PS points. Of course, there might be issues with resolution as well, which affect things, but it's mainly to do with coherence. Is it possible to combine descending and ascending images for PS InSAR? Yes, in a kind of post-processing way. So you have to really process the two sort of stacks of images separately. But once you've done that, you can try and combine the information. And typically that's what you might do if you want to separate out vertical and horizontal deformation. The reference point, the more coherent it is, the more stable it is over time. Can we assume that the most coherent point is a possible reference point? That's not a bad approach. And certainly, I mean, you can pick a reference point and then you can change it as well. So you can do all your processing with a certain reference point. But having done that at the end, you can just switch your reference, right? If you think, well, actually, this reference point is not in a stable area of ground, you can pick another one. So yeah, picking one that's very coherent to start with and somewhere in the middle is a useful thing to do as well, but it's not essential to be in the middle. So coherence is the most important. Is it possible to convert line of sight to VNH velocity? Yes, it is. I guess this may have been covered already. I think in the InSAR lecture, I should think. But essentially, was that correct, Melon?
Just partly, we didn't speak much. Okay, I think Tima mentioned about the northwards motion that is where we are not really sensitive to. But yeah.
Okay, well, I mean, briefly speaking, if it's vertical motion, it'll look the same in both the ascending and the descending, right? So if you add them together, this is a rough way of doing it, but if you add them together, you cancel out the horizontal and you're just left with the vertical. If you subtract them, you cancel out the vertical and you're left with the horizontal. Now, because incidence angles aren't exactly the same, you can do that slightly more accurately, but that's the basic principle. When utilizing passive corner reflectors for generating InSAR time series, which phase unwrapping algorithm is most suitable? So yeah, and what factors influence its selection in this context? So if you're using, corner reflectors are kind of your ideal PS, right? It's one really dominant bright scatterer. So these make great PS. So you can use a standard PS approach and it'll pick up your corner reflectors. But actually, typically, you can do even better if you do specific point-like processing. So you treat them as real points, and then you can do sub-pixel processing and so on, and get even better accuracy. So phase unwrapping, I'd say it's the same problem as in general, but if you have a network of these corner reflectors and you're processing them separately, you can look at the phase time series in time, and because the noise is very low, typically you can just unwrap it in time. Right, how are we doing for time? Speaking of time, we're running out, so I'm going to carry on. Apologies that I haven't answered your question yet. Okay, I'm going to talk about small baseline methods next. It'll actually be a lot quicker because this isn't so different from standard InSAR. So hopefully we'll get finished on time. Okay, so just to recap, I talked about the reason why we turn to persistent scatterers in the first place is because of decorrelation in time. But of course, it would be nice to use all these other non-PS, or what we typically refer to as distributed scatterers as well. So how can we do that? In general, if scatterers in this distributed scatterer move around, then we lose coherence. So what we do is we just make interferograms where we can minimize these changes. So that means minimizing the temporal baseline, so that minimizes the amount they move around with respect to each other. And we also typically try and minimize the change in look direction, which is to say, we try and minimize the perpendicular baseline as well. Not an issue typically for Sentinel-1, although that's starting to change lately, but it is for pretty much every other satellite. Okay, so you choose interferograms to make based on these small, both perpendicular and temporal baselines. If you're using really old data, you might have to worry about the Doppler baseline as well, but these days we don't tend to have to. So you make a network that might look something like this. So x-axis is time, y-axis is the perpendicular baseline, so the separation of the satellites at 2 different times. Yeah, and you make a network. So you connect up points, and you can see each of these gray lines, which represents an interferogram, is between points which are close in both time and baseline. Okay, so you make these interferograms. Typically, these interferograms are multi-looked. So that means averaged. So you lose resolution, but you increase signal to noise ratio. So averaged a bit in space. Then you unwrap each interferogram, typically in 2 dimensions. And then you find pixels. So these are your multi-look pixels that are spatially coherent in most interferograms. And you then invert them in some way for the temporal displacement. Okay, so the first 3 steps are actually, this is standard InSAR, conventional InSAR. Once we made our choice about which interferograms to make, then we just do normal InSAR, essentially. And it's only the last step that's different in any way. So this is quite intuitive, I think, to get a grip on. Right. There are different ways, I should say, to do this inversion. And these include singular value decomposition. So many of you will have heard of SBAS, and that's what the SBAS, or the original SBAS, uses. You can just do straightforward least squares. You can do some sort of constrained least squares, or you can do L1 norm minimization as well. And no doubt there are other approaches as well, but the idea is that you've got a whole network of interferograms, and you want to get a time series just with respect to one point. So that's the inversion step. Just a word on the AS in the term SBAS. And it's also in LIXBAS as well, which is the algorithm, one of the algorithms we produced at the University of Leeds, and NSBAS, which is a French algorithm. So the AS stands for AND subset. And what that means is that sometimes you might have a break in your network, right, such you have no interferograms that span a certain time period. There's an example given here. So all the blue interferograms are good interferograms, and the red ones are bad interferograms. And what this means is, because of these red interferograms, so that for some reason, these are not good interferograms, so there's a loss of coherence. It means you get a break in your network. Okay, so you have to make some assumption to be able to join these 2 sides up. So that's what algorithms which have AS in them actually do. Okay, so that's what SBAS does, it's what LIXBAS does, it's what NSBAS does as well. They use different assumptions, well, similar assumptions, but different approaches. And that means that SBAS, I mean, there is a specific algorithm, but I should mention that people often use it as just a general shorthand for small baseline algorithms in general. I prefer to use the term small baseline, but you'll often hear SBAS as a general approach, but really it's a specific algorithm that has to deal with these subsets. Okay, some advantages of this approach versus straightforward PS is you have some redundancy. Okay, so you make more interferograms than you need to invert for the time series. And that means you have redundancy. So if you have, for instance, these 3 interferograms, you can integrate around, and you can see if you take your unwrap phase and integrate around, and you should get back approximately to 0, of course, if you do that. And if you find you don't, and if you're close to 2 pi or minus 2 pi, then you can assume 1 or more unwrapping errors exist in some of these interferograms. So you can do this on a pixel by pixel basis, and you can decide to reject some interferograms, or just for that pixel to reject some interferograms, or correct them if you like as well. So that's a useful feature of this approach. Yeah, I'll come on to so as well as having differences because of phase unwrapping errors, you can get differences which are typically smaller than 2 pi due to decorrelation noise and also systematic biases, which I'll mention a little bit at the end. Okay, so here's an example. So the LIXBAS implementation of small baselines was done by Yu Morishita while he was at Leeds. And this is the original LIXBAS paper, a result from the original LIXBAS paper, which shows a comparison between InSAR results, which are the kind of small points in the background, and GPS or GNSS, which are the larger points. So these GNSS are just showing the deformation in the line of sight, so towards or away from the satellite. So they should be comparable, and indeed they are. You get very similar results. And you can also look at how these evolve over time. So there's a comparison on this bottom right panel between InSAR and GNSS, and also groundwater level, but it's the comparison with the GNSS that matters here. In general, it's quite good agreement. And note that this is very non-steady state in time. So there's no general requirement that your deformation has to be linear in time for small baseline approaches to work. Although where you have gaps, there is often an assumption, and there is in LIXBAS, that the deformation is linear over those gaps. So there is an assumption in there. Okay, looking at a larger scale, here are some more LIXBAS results. This is for Turkey. So here we have both the ascending and descending results. And this is an example where we have decomposed those. So we've calculated the east-west velocities. So these are just the average velocities. Again, of course, we always have an underlying time series, but just the velocities are being shown here. So yeah, you can decompose this into east-west and vertical, and this pulls out very nicely the active tectonics in Turkey, both on the North Anatolian fault. You can see the difference between the red and the yellow. I don't know if you can see my cursor, but if you can, I'm going along the North Anatolian fault. And then you can also see the East Anatolian fault running down here. So this is the difference between the red and the yellow to the eastern end of the image. And there's lots of vertical signals as well. Some are tectonic related, but mostly they're related to water. An even larger example is for the Tibetan Plateau. This was the image that was up right at the beginning. So the color here represents the eastward velocity from InSAR. So again, we've done ascending and descending and decomposed. And this, this really involves a lot of interferograms because, well, is there a scale there? Yeah, you can see a scale bar showing 250 kilometers. So this is hundreds and hundreds, thousands and thousands of interferograms that have gone into making this. Or hundreds of thousands, I should say. Okay, there are a few maybe variations on the small baseline approach. One involves trying to unwrap in 3 dimensions, so that can improve the accuracy. There are different approaches to that. Working with single look images, although multi-looking is commonly applied, you can apply this to single look pixels as well. Okay, there's going to get to stamps. Stamps is something I developed and other people have worked on since. So stamps was originally a persistent scatter algorithm, but there is a small baseline approach in there as well. And it's basically the same as the PS approach, but it's just applied to small baseline interferograms rather than single master. Okay, I guess the reason I mentioned that is because you can kind of compare how do the two different approaches do if you process both at full resolution, and the answer is you get very similar results. So this is one example showing processing with persistent scatterers and also with small baselines, and you can see that they look superficially very similar. There is a difference in the number of pixels, so there were many more small baseline pixels, so distributed scatterer pixels picked than PS pixels, as you might expect. But note also that a certain number of those, so that's shown by the green bars here, were picked by both approaches. So it's not clear cut, right? There's no clear cut difference between PS pixels and small baseline pixels. You know, the most point-like should be PS, and the most fully distributed one should be small baseline, good for small baselines, but there are plenty which lie somewhere in the middle. I think I'll just skip over this one for now. Okay. Oh yeah, one other important approach to mention is phase linking, also known as triangulation or squeeze-SAR. Again, squeeze-SAR is a specific implementation of this approach, but the general term is I would say, phase linking. So some people might think of this as a sort of third time series approach. But really, I think of it as kind of a pre-processing step that you can apply prior to standard time series techniques. So the idea is you're trying to get signal from distributed scatterers. What you do is you make, well, in the ideal case, you make all possible interferograms. Okay, so you make a lot of interferograms for this to work. In general, you don't actually have to make them all, you just have to make a lot. So you make a whole bunch of interferograms, and what's shown here is the so-called coherence matrix. So image number just represents this is for 25 images shown on both axes, it's the same. And then the color is showing the coherence. So this could be for the average coherence of the whole interferogram, but you actually do this for every single pixel. So I think this example might be for individual pixels. So you calculate the coherence for multiple pixels individually. And then what you can do is you can take this coherence matrix and you can sort of compress it, which is, so to say, what you actually do is you invert all of these phases to get a single primary time series instead. Okay, so it's what we do in the small baseline approach. But that's in the small baseline approach, we do it after processing, so after phase unwrapping and so on. In this case, it's done earlier, it's done on wrapped phases, and it's also done on not just small baseline interferograms. So there's actually information in all interferograms, although, of course, as you completely lose coherence, the amount of information becomes very minimal. So you make more interferograms, and based on the wrap phase, you invert for a single master time series. That's the pre-processing step. Once you've done that, you can just apply what is basically a PS algorithm, right? So you have a single master time series. Hopefully the results you have are now much more coherent, right? Even if you're working on distributed scatterers, because of this inversion step, you end up with a coherent time series for many more pixels, and you can just apply a kind of PS type algorithm to this. So there are some references given below if you want to look into this. I guess this was originally developed by Guarnieri and Tabaldini, this approach. Okay. One word of warning, just before I finish, is about a so-called fading signal or a phase bias. So what we found is, especially working with Sentinel-1 data, is we often get lots of signals which nearly always are substance, or they look like substance, but they're not actually related to substance. So that's why it's referred to as a phase bias. So it's adding this bias which looks like substance when actually we're not really measuring substance of the ground. So this mostly affects croplands and forested regions, and it's due to both soil moisture changes. That's perhaps the better understood part, but it can also be due to vegetation changes as well, and this is not quite so well understood. So both of these things can contribute to a kind of spurious signal. And the reason we notice it more in Sentinel-1 is because it's much stronger when your temporal baseline is short. So when we were working with, back in the day with MVSAT or ERS, over 35 days, most of the signal has gone. It's faded away. That's why it's called a fading signal. What that actually means in practice is the signal becomes more and more incoherent, such that eventually it's not contributing at all. And because it affects short temporal baselines, it really affects the small baseline approach, of course, when we're trying to pick just those smaller baselines. Persistent scatterers and phase linking approaches are hardly affected. So this is quite a good argument for using phase linking, even when you're working with distributed scatterers, is you can really reduce the effect of this phase bias. But you can identify it. So you can identify it most easily, I guess, by coming back to these phase loop closures again. So if you take 3 interferograms and integrate, so that, again, this is on a point-by-point basis, so a pixel-by-pixel basis. You integrate around 3 interferograms for that pixel, then it should come back to approximately 0. It won't for a number of reasons, one of which is a phase unwrapping error. But if you've ruled out phase unwrapping errors, the other 2 contributions are phase noise and also this bias. So phase noise could go both ways, but phase bias will essentially nearly always go just the same way for that pixel. So if you take the mean phase loop closure, sorry, the mean absolute value of it, you can identify quite well where you've got this fading signal affecting it. And one thing you can do is just mask it out. So that's an option. LixPass. Another thing you can do is try and correct it. So that there is an empirical approach to this. Well, this is probably the only empirical correction approach. But other approaches tend to just avoid the problem by masking them out. Okay, so it's important to note when you're working with small baselines that you may well have phase bias in your image as well. Okay, so that brings me to the end. I don't have a long summary, but I tried to wrap up with maybe a few salient points. So I talked about 2 main approaches: persistent scatterers and small baselines. So persistent scatterers, these are pixels that have low decorrelation of a whole time series, essentially. Whereas if you have distributed scatterers, so those which decorrelate over long time periods, then you have to use a small baseline approach. But in both cases, they're both time series approaches, and we can then do modeling and filtering to reduce non-deformation signals. I suppose if you're thinking about which approach to use, things to think about are you working in an urban environment, and do you want the highest resolution? And if you do, you want the highest resolution in an urban environment, then PS techniques, that's the approach. A more general approach is definitely small baselines for rural areas and in cases where you're not really worried about resolution. Okay, so yeah, final chance for questions and answers. Just going to stop so I can actually see people. Okay. Any questions from the in-person audience?
Still no hands up, which is okay. There is one question.
Yeah, I have actually 2 questions. First question is, if I am going to run a smart process, what is the best approach? How do we discard the bad interferogram? Should we discard the bad interferogram altogether, or should we mask the low coherence areas? For example,
I think I missed one word there. So which interferograms should we discard?
yeah, for example, if we have a bad interferogram, let's say more than 50% of the interferogram has low coherent pixels. Should we discard that interferogram altogether, or should we mask out low coherent areas?
Ah, okay. Yeah, so you're always faced with the situation where you have variable coherence. So some interferograms might have very good coherence and some will have lower coherence in general, and maybe some areas where it's complete decorrelation. So I would say it depends a little bit on your approach, right? So if you're only keeping pixels where you want to have a connected network over the whole time period, so no gaps, then you should probably throw out the worst interferograms, because that's just going to, it could throw in gaps if you're not careful. But if you're taking a more general approach where gaps are fine, then in principle you can keep them in, and on a pixel by pixel basis you can decide, yeah, this interferogram is coherent or not, and then use that in the inversion for that particular pixel. So yeah, it depends a little bit on your approach, I would say, but in general there's no need to throw them out. So in LixPass, the worst interferograms do get thrown out, but there is an option to keep some which are not great, but they still have coherence for some pixels, because it can contribute to the phase time series for some pixels and not for others.
So my second question is, if for example I have 1000 interferograms for my S-pass process I'm going to run, what can be the automated approach? How we can discard the interferograms that don't fall in our predefined criteria? For example, can we say that drop all interferograms that are having 20% pixel having values less than 0.2 of the coherence, like this?
Well, you should really ask Milan this question, because he works with these with LixPass on a daily basis. I would say, generally speaking, you can leave them all in, and LixPass will throw them out for you. Is that a fair answer, Milan?
Yep. Let's catch up during tomorrow's practical.
Yeah. Okay. There I go to
question here. Yeah.
My question about the validation of the results. So we saw in some of your slides that you validate the results of the time series analysis with, for example, GPS points or in situ data. My question is that when we have like this ascending and descending approach, so to measure the deformation in the line of sight, we have more points, so it's more convenient to compare it, for example, with the in situ or GPS data. But the problem is that we have like the vertical displacement using GPS data, but here we have the line of sight measurement. So how we bring these two actually together? And if we go from the ascending and descending to the vertical displacement measurement, then we have to do some modeling, and then we won't have so much of the points. So what would be your take on this?
Yes. Yeah, so I would say, first of all, if you just want to do validation, the better approach is to map your GNSS into the line of sight. So of course you start with 3 components and you reduce it to 1, but then you can compare it directly to the InSAR. So you can look at your ascending and descending separately and validate that using the GPS. So that, for validation, that's a better approach than, as you say, first of all, decomposing into vertical and so on, because there are assumptions that go into that. Yeah. So by the way, I think that figure I showed from Yu Morishita's paper, that was that case. So the GPS there had been mapped into the line of sight. So it's just the component in the line of sight. And the comparison was then between the InSAR directly and that component. Okay. I'll try and answer a few of these questions. And I think looks like Pedro is having a good go at answering them as well, so that's fantastic. Okay, so I'll come back to, there was a question asked even before I started talking, which is, how does InSAR time series analysis help in monitoring land deformation in multi-hazard scenarios, such as combined risks of landslide, subsidence, and earthquakes? And what are the main challenges in applying InSAR time series for large-scale hazard-prone areas with diverse terrain types? That's, I mean, it's a good question, and it's very difficult to answer that in a short way. I mean, clearly we do use InSAR for monitoring hazards, and it's often the case that people are just considering one hazard, but actually you can't avoid it, right? So whenever we look at tectonics, we end up seeing subsidence as well. We end up seeing landslides, in some case volcanic deformation as well. So you can't actually avoid it even if you want to. I mean, there are multi-hazards being typically present in the interferograms we look at. So it's really a question then of how you interpret the results, I would say. And the main challenges, well, there's lots of them. Probably the main one is actually decorrelation due to vegetation and snow, ice, things like that. So, or water. So areas where we just can't get good signal is probably the main challenge. And after that, it's probably dealing with atmosphere. Okay, how to advance PS algorithms such as SqueezeSAR improve upon traditional PS methods. Yeah, so I think I talked about that. What are the computational challenges? It is more computationally challenging to use an approach like that. So you have to make many more interferograms in the first place, although in principle that's not as hard as it sounds. But then this inversion step is actually quite time consuming as well. So inversion of wrapped data is difficult. So yeah, there is a cost to it. Is there a way around estimating slow subsidence in areas where we have a few months of low coherence using SBAS? Yes, there is, and that's essentially by making assumptions. So if you can't, well, ideally you can make an interferogram that covers that period of low coherence. Okay, so if you have snow on the ground for some time and it goes away again and your coherence recovers, then you can still make an interferogram covering that, and you've got no problems really. But if you can't do that, then you have to make some assumption, such as, you assume that the deformation is linear over that time period. So you look at the deformation before and after, and you can make an assumption. Okay, what is the best method for the forest area? Yeah, there isn't one really. You might be lucky if it's a forest that has coherence sometimes, like in the winter. You can still use a small baseline approach. But if it's tropical vegetation, tropical jungle or something, then probably all hope is lost. You could try L-band, I guess. How can GPS data be used to improve PS results in rural areas? Oh, that's a good question. Yeah, I don't know. It's a interesting thing to think about. Typically, we're using GPS for validation, so that's useful in its own right. But to actually use it as part of the processing, I haven't thought too much about that. But yeah, good question. Is there any way to increase the number of points to have more information of the area? Maybe the interpolation is the only way. Yeah, I mean, you can't, where there's no information, you can't get it, of course, directly. So in that sense, interpolation is the only way. And that's just making an assumption that, what you have in the missing part follows the same pattern of other parts. The whole point of these time series approaches, I guess, is to try and extract the information. So there's a little bit of coherence and you can still extract it. But if there's really no coherence, if there's really no signal, there's nothing else you can do. Okay, given the time, I'll just answer one more question, then I'll let you go for beers or whatever it is you're doing now. What quantitative metrics can be used to assess the spatial correlation of deformation signals in InSAR data? And how do these metrics influence the selection of PS candidates? So I mean I'm not entirely sure what the question is asking. If you don't have spatial coherence of deformation signals, then all these approaches that rely on spatial correlation aren't going to work. That's true. So if let's say you have one PS point that is behaving completely differently to points around it, then it'll be very, well, I always say it won't work. It's less likely to work if you use spatial correlation PS approach. And it's more likely to work if you use the first PS approach that I mentioned. I'd say this only is an issue for persistent scatterers. If you're doing multi-looking anyway, if you haven't got spatial correlation, then your multi-looking is not going to work, right? So yeah, for PS, if you've really got that situation, then you're better off with the first approach. Having said that, I've seen plenty of plenty of occasions where spatial correlation approach still works because the difference, if the deformation rate is small, then the difference is small and you can still extract it. Okay, I think I'm done. Thanks for hanging with me through that long session, and thanks for your questions as well.
Thank you very much, Andy, for also the extended talk. You spent some 10 or 15 minutes more than
Sorry about that. I was answering questions, I think, rather than the talk. But yes, sorry. If you should tell me to stop next time if it's a problem.
No,
I'll let you get off. Thanks a lot.
Yeah. Thank you.
Thank you, everyone. Bye.
Oh, that was quick. Okay. So first of all, almost the last of all, I want to thank the online attendance. I'm aware that there are still some 22 unanswered questions. Yeah, I will have a look. Maybe some very fast answer can be still done in the next 5 or 10 minutes. But we apologize if there is some really hot question that was not answered. Please write us the question using email. Or if you saw some other means, I think this year we didn't use any chat application, so perhaps the email will be the best way where we can really do what we can to help answer the questions. And that's it for the online participants. I thank you very much and see you tomorrow, where we will start by the Leeds Pass information and tutorial. You have the schedule, so I'm closing the recording now and closing the Zoom, and see you